Hello and welcome back to Math 1500 Applied Business Mathematics, Connecticut State Community College. Today we're going to be looking at probability, section 8.3, probability and probability models. Basically, probability is simply talking about the likelihood of an event occurring. The expected probability of an event occurring can be based on experimentation or theoretical expectation. One of the things with probability is it's likelihood. It's not a guaranteed. If the probability of something happening is likely, it doesn't mean it's going to happen. If the probability is unlikely, it doesn't mean that the event can't happen. Okay. In our previous video, we looked at relative frequency tables based on observed results. Today, we're going to be talking about theoretical probabilities. So, for example, if I expect that the probability that I flip a coin and it comes up heads is 1 out of 2, if I flip a coin 10 times, I may not get heads exactly 5 times and tails exactly 5 times. That would be observing what happens and basing our conclusions on observed experimentation. In this video, we're going to be talking about the likelihood or the theoretical probabilities. Okay? A probability model for a particular experiment is the probability distribution that predicts the relative frequency for each outcome. So let's look at some examples. First of all, a fair coin is flipped once. My outcome is heads or tails. So my sample space would be heads or tails. That's what can happen. A fair coin is flipped twice. Now, something that I've not seen in our textbook that I like to use is what's called a tree diagram. In a tree diagram, on the first flip, the coin could come up heads or tails. On the second flip, the coin could come up heads or tails regardless of what happened on the first flip. Therefore, I have 4 outcomes: heads, 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 tails, tails, heads, and tails, tails. Now, these outcomes are all equally likely. Flipping a coin, heads or tails, are equally likely. So here, because the outcomes are equally likely, the probability of flip a coin and comes up heads is 1 out of 2, because one of the 2 outcomes is heads. So the probability of heads would be 1 out of 2. Down here, the probability of getting heads both times would be 1 out of 4. The outcomes are equally likely. Getting heads once is 1 of the 4 outcomes. Okay? I'm sorry, getting heads twice is 1 out of the 4 outcomes. What if a fair coin is flipped 3 times? Again, I'm going to use my tree diagram. The first flip, we got heads or tails. On the second flip, the coin came up heads or tails, regardless of what happened on the first flip. On the third flip, the coin came up heads or tails, regardless of what had happened before. So my outcomes, which are all equally likely because of flip of a coin, it's 1 out of 2 for heads or tails. So my sample space would be heads, 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 tails, heads, tails, heads, heads, tails, tails. That's from the first diagram: heads, 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 tails, heads, tails, heads, heads, tails, tails, and now tails, heads, heads, tails, heads, tails, 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 heads, and tails, tails, tails. Okay? A fair die is rolled once. My outcomes are 1, 2, 3, 4, 5, 6. So my sample space would be 1, 2, 3, 4, 5, or 6. Now, if a fair die is rolled twice, depending what you talk about as outcomes, they're equal or not. So if I roll a die twice, I like to set this up this way. If I roll 2 dice, my outcomes could be a sum of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. However, for each of those to occur, To get a 2, you need a 1 and a 1. To get a sum of 3, you need a 1 and a 2 or a 2 and a 1. To get an outcome of 4, you need a 1 and a 3, 2 and 2, or 3 and 1. So you notice that the likelihood of getting a 4 with 2 dice is greater than getting a 2 or a 3. To get a 5, I need to roll a 1 and a 4, 2 and a 3, 3 and a 2, 4 and a 1. And I'm going to keep going and generate this table. 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. So I jumped ahead, and here you see the completed table. Notice that there's 1 way to get a 2, 2 ways to get a 3, 4 ways to get a 4, 3 ways to get a 4, 4 for 5, 5, 6, again, 5 ways to get an 8, 4, 3, 2, and 1 way to get a 12. There are 36 total possible outcomes. Okay, so the probability of rolling a die and getting a 2 would be 1 out of 36. To get a 3 would be 2 out of 36, and so on. And so you can see that the probability model is set up where a 2, I'm likely to get a sum of 2, 1 out of every 36 rolls. I'm likely to get a sum of 7, 6 out of 36, or 1 out of every 6 rolls. So there's a probability model with dice as well as coins. Okay. Addition principle. What's the probability of A union B? The probability of A or B. This showed up in a previous video. Okay, and you're going to see it again here. What's the probability that an athlete plays football or baseball? That's the probability that they play football plus they play baseball, but I have to subtract out those who play both. So the probability of A or B is the probability of A plus the probability of B. But then I have to subtract the possible overlap, the possible situation where there are outcomes in both categories, in both sets. If the outcomes A and B are mutually exclusive, then I don't need to worry about the probability of A and B because it would be 0. So let's look at an example, a couple of examples. At a local community college, a survey found that 60% of students take in-person classes, 30% of the students take online classes, and 15% of the students take both in-person and online classes. What's the probability that a randomly selected student is taking in-person or online classes? Now, in a previous video, we used a Venn diagram, and I'm going to do a Venn diagram here. And rather than writing the percents, we're going to assume for each 100 students. So we have our in-person classes, and we have our online classes. Okay, and I'm going to start with 15% of students take both in-person and online classes. So that would be 15 out of every 100 students are in the overlap here between in-person and online. Then you'll notice that 60% of students take in-person classes. So this whole green circle is 60%, or 60 out of every 100 students. But 15 of them are already here. So this would be 45 students take in-person but not online classes. Then you notice that 30%, or 30 out of every 100 students, are taking online classes, but 15 of them are already in the overlap, so the other 15 are out here. So one way I could find this, what is the probability that a randomly selected student is taking in-person or online classes? I could add up the 45, the 15, and the 15, which is 75 out of every 100 students, or 0.75. So the probability that I randomly select a student and the student is taking either online or in-person classes or both is 0.75. The other way I could have done it is I could have said I have the 0.60 because 60% of the students take in-person classes plus the 0.30 because 30% of students take online classes, except that I counted this 15% of students twice. So I need to subtract it off once so that I only count those students once. 0.6 plus 0.3 minus 0.15 is still 0.75. Okay, so that's the union, the probability of OR. Just another example here with some numbers to play with. Remember that the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. And I just gave you some numbers here that A union B is 0.75. The probability of B is 0.60. And the probability of A and B is 0.20. Find the probability of A. And it becomes just a very simple algebra problem. 0.75 equals the probability of A plus 0.40, because 0.60 minus 0.20 is 0.40. Now when I subtract the 0.40 from both sides, 0.35 equals the probability of A, or I'm going to rewrite it, the probability of A equals 0.35. So that's just being able to play around with the formula and the probabilities. Most often we like to situate our data in a table. And again, this table comes courtesy of our textbook, so again, all credit there. And the following table shows sales in millions of items of Macs, iPhones, and iPads sold by Apple in 2012, 13, and 14. Okay, so you'll notice Macs, okay, in 2012 we sold 18 million Macs, were sold 1619 for a total of 53 million Macs were sold over that 3-year period. And you can read the rest of the table. In 2013 Apple sold 16 million Macs, 150 million iPhones, and 71 million iPads. Okay, so if one of these 695 million items sold is selected at random, find the probabilities of the following events. Okay, what's the probability that I randomly select something and it's a Mac? Well, there are 53 of the 695, so 53 over 695. So that's my probability. 53 divided by 695 is 0.0763. I insist always that probabilities are written to 3 or 4 decimal places. If one of these items is selected at random, what's the probability it was sold in 2013? Well, in 2013, 238 of the 695 million items were sold. So 238 divided by 695. So this comes down to reading a table. So 0.3424. Now what's the probability that the item that I randomly select is a Mac sold in 2013? A Mac sold in 2013, that's an AND. So that would only be 16 of the 695 items. So 16 divided by the 695. 0.0230. Now I'm going to be doing some scrolling up and down, it appears. What's the probability that the item that's randomly selected is either a Mac or was sold in 2013? So a Mac or sold in 2013. Now the probability that it's a Mac is 53. The probability of 2013 is 238. However, I need to subtract the 16 Macs that got counted twice, and that all has a common denominator of 695. So 53 plus 238 minus 16 is 275 over 695, which is 0.3957. So that's the probability that the item randomly selected is a Mac or was sold in 2013. Now, what's the probability that the item that was randomly picked is not a Mac? Well, Mac was 53. So that's going to be 695 minus 53 over 695, because of the 695 items sold, 695 million, 53 million of them were Macs. So the other 642 of the 695 million items were not Macs. And so that would be 0.9237. And if you'll notice, question A, what's the probability that it is a Mac? E, what's the probability that it is not a Mac? Those two, 0.0763 and 0.9237, should add up to 1, because there's no option, either is or is not a Mac. Okay, so another quick look at probability models. The videos in this section are going fairly quickly. I trust that you are keeping up with the homeworks. Again, if you have questions, please feel free to reach out to me. And as always, I will see you next time.